Okay, so now we can represent y is equal to cosine of c times sine of omega naught t minus delta plus f naught cosine of omega t m omega square minus omega square, where we already know that c is equal to under root of a square plus v square, and delta is equal to tangent inverse p over a. Okay. Here in this case, we know that this term, this second term, which is related with the particular solution, we can get a maximum cosine omega t will be equal to 1. The maximum value of cosine is 1. So in that situation, when cosine of omega t is equal to 1, then we call its factor as a naught, okay, which is equal to f naught over m omega naught square minus omega square, or it can also be written as f naught over k times m 1 minus omega over omega naught square. And if we represent this term by rho, so which is called as the resonance factor, then this a naught can be written as f naught over m rho, k rho, f naught over k rho. So we take a naught is equal to f naught over k rho, because rho was here, and this when we can talk about the resonance. Resonance is a condition when the frequency, which is represented by omega over 2 pi actually, but we can just, because 2 pi is constant, so we can just say that omega can be represented by the frequency. Frequency can be represented by the omega. So when the frequency of the driving force approaches omega naught, then both terms are almost equal. So then this denominator is very small. So this value of rho becomes very large. When value of rho becomes very large, then the a naught, which is the which actually represent the amplitude of the driving force oscillation, also become very large. So in this case, that situation is called as the resonance situation. To further discuss the resonance in this case, we can look at the original equation m. So m y double prime plus c y prime plus ky is equal to f naught cosine of omega t. Okay, since now in this case we are considering very negligible damping, so it is my double prime plus ky is equal to f naught cosine of omega t. So for the resonance situation, omega will be equal to omega naught. That means for resonance, okay, so for resonance it is be omega is almost equal to omega naught. Okay, omega is almost equal to omega naught. So therefore in this case k over m is also omega, so it actually like this plus omega square y and f naught cosine of omega naught t. So this will be this will be omega, because k over m is omega. Okay, f naught over m. F naught over m cosine of omega t. So now if we look at this situation, in this situation the solution of this homogeneous part also involves cosine of omega naught, and the solution of the particular part also involves cosine of omega naught. So therefore the solution of the particular part according to our modification rule will involve t. Okay, so for example, the general solution in this case, it will not be a cosine omega naught t plus b sine omega naught t, rather it will be multiplied by also t. Okay, so this can be verified that in this situation, okay, I will not derive it, but you can verify that in this situation a will be 0 and b will be f naught over 2 omega naught m. Okay, so the particular solution will then become, in this case, because a is 0, so particular solution will become f naught over 2 omega naught m sine omega naught t. So in this case omega naught t, and then of course it will be multiplied by t. So since the particular solution is being multiplied by t, so if I will plot it, then this graph will be something like this. So it will be something like this. So with the passage of time, the amplitude will become increasing and increasing. Okay, so since this is an undamped situation, and then the driving force frequency is naturally is almost equal to the natural frequency of the system. So in the case of the resonance, then the amplitudes of the motions will keep increasing in both directions. Actually, one comment I want to make over here is that you don't have to memorize all these formulas as a result of these derivations. Only the basic concept of the homogeneous and non-homogeneous solutions is necessary to solve the problems in this case. So therefore, I would not recommend remembering any of these formulas. So remember that this above was the undamped forced oscillation. It means that when C was equal to 0. Okay, so when C is not equal to 0, so we can do a similar kind of process. Okay, so that will be the damped, okay, damped forced oscillation. It is not necessary to repeat all those calculations. Rather, the application of these equations is quite simple. So maybe we can see some of the examples, okay, instead of doing this theoretical work. Okay, so examples will be, with the examples it will be much easier and much easier to understand, and we will be very much confident about these terminologies. Okay, so I will solve a few examples now. Okay, so suppose we have this equation, this one, 0.5 y double prime plus 1.2 y prime plus 2 y is equal to 5 cosine 40. So we can interpret this equation as a mass spring system with the forced oscillation. So in this case, the mass of the system will be in, if for example, if we take the units in SI system, so mass of the system will be 0.2 kilogram. The damping force will be 1.2 Newton per second. Okay, and the spring constant will be equal to 2 Newton per meter. Okay, so this will be the data. This will be the data we can interpret from this equation. Well, that is not all actually. Yeah, one correction. In the units of C, the damping constant are in kilogram per second. Okay. So we have to be consistent with it. And also we can see that the F naught will be this 5. It will be 5 Newton, and 4T represent the omega T. So omega will be equal to 4 cycles per second. Okay, so 4 per second, hertz, which is also called as hertz. So this is the data we can interpret about the mass spring system. So maybe the question can be the interpret it for mass spring system. So with this we can solve it. So for the homogeneous equation, 0.2 y double prime plus 1.2 y prime plus 2y is equal to 0. We have the characteristic equation in terms of m is 0.2 m square plus 1.2 m plus 2 is equal to 0. And then this can be solved by the quadratic formula, or we can even factorize it, whichever is easy for you. So minus 1.2, I use the quadratic formula here. So it will be 1.2 square minus 4 into 0.2 into 2, and then divided by 2 times of this 0.2, 2 times into 0.2. So the solution of m will return in 2 values. So the term in the under root square root term is the integral, it will be minus 0.16, and then this will be 0.4. So we can further simplify into this is minus 1.2 over 0.4, so it will be 1.2. So it will be minus 3, minus 1.2 over 0.4, and then it is because it is 0.16, the square root of 0.16 is, so it will be plus minus 0.16 square root is 0.4. So 0.4 divided by 0.4 is 1. So it will be plus minus I. Okay, so minus 3 plus minus I will get. So this will give us the homogeneous part of the equation, of the solution equation. So that will be, because alpha is minus 3, so it will be e power minus 3t times cosine of, because now beta is 1, cosine of t plus sine of t. Sine of t. We need to use the arbitrary constants as well. So this is sine of t. So b was 1, and then a also will be there. So a cosine of t plus b sine of t. Okay, so this is the homogeneous solution. For the particular solution, so because the term over here is cosine of 40, and then it is not common in with this, so therefore we will not need to apply the modification rule. So we will just stick with the basic rule. So the particular solution will be because now we have used a and b, so I can use c cosine of 40. Yeah, c cosine of 40 plus be